Okay, so we just went through and we talked about the three different scenarios of how waves can be produced by different types of devices. There's the string, pipe open at both ends, and the pipe closed at one end. The pipe closed at one end is sort of bizarre because there's only certain frequencies that are allowed. The reason is that since you always have to have a node at one end and an antinode at the other, if you were to double this frequency, or cut the size of the wave in half, you would have to have either nodes at both ends or antinodes at both ends, and that's not going to work. So you can only fit multiples of a fourth of a wave inside the pipe. So you could fit a fourth of the wave, or 3/4 of the wave, or 5/4 of the wave, because you always have to have that sort of dangling quarter of a wave to make the antinode at the end. So the rule is you can only have odd harmonics for a pipe closed at both ends, or a pipe closed at one end. I'm sorry, the pipe closed at both ends would just be a can. So the rule is they have to be odd numbers. So we kind of look through and sort of sketch them. First fundamental for a string, or fixed at both ends, nodes at both ends, would be where you have, it kind of goes like this. And then for the second harmonic, it would be half the size. So it goes up and down, but the frequency would be twice as high. Okay, for third, it would be up, down, up again, and still a node at the end. And we can kind of remember this from our string lab. So you get the idea of what's going on here. For one that's fixed, we'll do this one last. If it's open at both ends, it's got to have an antinode here and an antinode here. Okay, so it ends up looking kind of like two halves of a wave, but it's still the same length as this one. Okay, you could do the second harmonic the same way, but you have to put up, down, up. Okay, and you realize that, okay, that's really, here's one half of a wave, and here these two parts make the other half of a wave. Okay, so we can, then the third harmonic, I'll do one more here. Up, down, up, down. So really all of them are allowed here. Okay, see, we got one full wave here, and then two more quarters of a wave. So you got 2.5 waves, just like, or I'm sorry, 1.5 waves. Just like here's one wave, and then there's another half wave. So really it's the same pattern for the string and the pipe open at both ends. The one that's closed at one end is going to be different. So you have always a node at one end and an antinode at the other. And so there's no way to make this twice as long without putting a node at both ends. So there is no second harmonic for that. We just have to go right to the third harmonic, the next odd one. Okay, so you realize, and then this would be 3/4 of a wave. Okay, so I can show you the relationships for these. There's an equation describing all three of these different relationships. The first two are almost the same. So for the waves on a string, the frequency of a certain harmonic, or the nth harmonic, is whatever that harmonic number is, times the speed of sound for the string, divided by 2 times the length of the string. Okay, and so you realize, oh, the second harmonic, I'm just going to put n equals 2 in here, and I'm just going to double that frequency, double that fundamental frequency. For the third one, I'm going to triple it. It's the same equation for a pipe open at both ends. The only difference is now we're talking about the speed of sound and the air going through the pipe, not through the material itself. So for a string, it depends on what the string's made out of and the tension on the string and things like that. But for the pipe organ or whatever is making that, it has to be just the speed of sound through the air is what makes that. So that's somewhat temperature dependent. We already talked about that. The last one is sort of the bizarre one, the one where you can only have odd harmonics, pipe closed at one end. So it says, notice how this is counting 1, 3, 5, 7, so you can only have odd numbers because of that weird open and closed part. Again, it depends on the speed of sound in air. But since now instead of half waves, we can fit in there fourths of waves, the equation changes just slightly. Okay, so the first two have to do with multiples of a half wave, or a half of the length of the pipe or the string. This one has to do with a fourth of the length of the pipe or string. So I wanted you to work through a couple different combinations I have here in your worksheet. So I give you all three of these relationships at the beginning, and I want you to kind of work through what are the frequencies on a string, and pipe open at both ends, and a bottle, which is a pipe closed at one end. And so for the first one, I give you some parameters, so the speed of sound on the string and the length of the string. So you should be able to figure those things out to figure out the fundamental frequency. And remember that the harmonic number, if you know the fundamental frequency, if you know this frequency, these are always just going to be whole number multiples of that. So this should be 6 times, since this is n equals 6, this should just be 6 times the fundamental frequency. It's the same goes for every situation. The only difference is for the bottom one, since it's a closed at one end, we can't have even harmonics. So, but it's still true that the fundamental frequency should be, if this is the fifth harmonic, it should be 1/5 of that should be the fundamental frequency. So I'll let you guys work through this, and this will be our only task for the week other than viewing these lessons.